All right, good morning, everyone. How are you all doing? I'm glad those of you that are here were able to make it here. It's crazy outside. I don't know if anyone else commuted, but it was accidents on every road. It took me an extra 30 minutes to get here, which was insane. Anyway, so I'm really glad you all are here and you all are safe. Does anyone have any questions before we get started? All right, dope. Let's roll into our new content. So the first part of the semester is really just getting at the language of organic chemistry, understanding how our organic chemists talk so that we can all share the same communal language. So before we get into our key reactions, I think it's important to highlight that a lot of organic chemistry is actually just repetition. It all kind of boils down to the same three main reactions, or it's the same just general trends. So in order to help highlight that, I kind of do this little aside, a brief part of chapter 3, where we're looking at just our fundamental parts of what is an organic chemist, or what is organic chemistry. So that's what we're gonna do, is we're gonna outline just some really basic overarching trends that we're gonna see through all of organic chemistry. So it's going to be things like, what is a nucleophile? What is an electrophile? What is addition, substitution, and elimination? And we're gonna look at what all of these reactions are so that when we move into the details, hopefully we don't lose sight of the big overarching trends. Because a lot of people find that organic chemistry is a lot of memorization, and that they feel like they get overwhelmed because there are a lot of details, and there are a lot of details. But if you can find the similarities and differences, then it's gonna be a lot easier, because then you can find the patterns. And it's that pattern recognition that's gonna make organic chemistry really approachable and actually easier. So that's what we're hoping for this bit of our notes, is to find those patterns, to make sure that we're all getting comfortable with seeing that pattern recognition. All right. So we have two main ways to break our bonds. There is heterolytic cleavage. That is our most common. So heterolytic meaning uneven breaking. That's where one atom takes both electrons from that bond. So you would end up with your cation and your anion. You get ions from this. That is our most common. It's where you have that full-headed arrow. That is where you are creating ions. That is what we're going to do for most of the semester. So that's what I want you to generally do. That is what's most common. We also have homolytic cleavage, homo meaning same. So we are going to have even breaking. That is where each atom of the bond takes one electron. So we are evenly breaking that bond. That is creating radicals. That uses those single-headed arrows, or they're sometimes called fish hooks. So it is that one electron, showing that one electron is going each direction. This is less common, so much less common that we are not going to do these arrows again until the very end of the semester. It'll be our last lecture is where we're going to do this again. Because I used to do this at the beginning, and students then tried to do radical arrows through the entire semester. It's not the common one. The common one is where we have that uneven breaking. That's more common. That's what we're going to typically do. So be aware of the fact that there are both, and that these arrows have very different meanings, but the one that we're going to do most of the semester is that heterolytic cleavage. That's the major way that we do things. So with our bonds, to know which bond you're going to break the weaker bond. Weaker bonds are the ones that are more reactive. They're also going to be the ones that are longer. The shorter your bond is, the stronger it is. The longer it is, the weaker it is. When you look at the size of the orbital overlap, your stronger bonds will have better orbital overlap. they'll have the same size orbitals, meaning that they're in the same row or period on the periodic table. The farther down on the periodic table, the longer they are. That's a Gen Chem concept that still applies, is knowing that relative length of the bond based on the fact that your atoms are closer or in the same row on the periodic table. That means they're in the same energy level. They have the same general size orbitals. That's better orbital overlap. That's our stronger bonds. Those are going to be harder to break. So when we look at reactive bonds, in general, these stronger bonds are less reactive, meaning that they are more stable. And this is a general trend that we're going to see over and over and over, where as you are decreasing your energy, that means that you are increasing your reactivity, which is decreasing your stability. So you lower the energy, that is, or wait, hang on. I flipped those, sorry. As we lower our energy, we are increasing our stability, we are decreasing our reactivity. Because as you increase the reactivity, you're higher energy, you're more likely to react. When you are lower energy, that means you are more stable, less likely to react. And that's what we're seeing, is that the weaker bonds are going to be the ones that are more likely to react, more reactive, less stable. What that also means is that they're going to lead to, and this is just saying radicals, but it applies to our intermediates. The less stable bond will lead to a more stable intermediate, or a more I did that backwards, sorry. The more stable bond will lead to a less stable intermediate. The more reactive bond leads to a less reactive intermediate, or it's easier to talk about in terms of stability. Less stable to start out leads to more stable intermediate. If something is happy where it is and you force it to react, you're going to make an intermediate that's more reactive. It's going to be higher in energy. So if you start low energy and you force me to react, I'm going to make a high energy intermediate. If I'm already high energy and I just react because I want to, I'm going to go to a lower energy intermediate. That's the idea, is that if you are high energy to begin with, you're going to go to a lower energy intermediate. If you are low energy to begin with and you have to react, you're going to go to a higher energy intermediate. Right? You're going to make something that is less stable. That's our general trends that we're going to see. I'm showing this with radicals, but it applies 100% to our carbocations as well, where what we see is that methyl, so that is actually methane, is that it is going to create a methyl radical, and that's about 105 kcals per mole. Cool. That number you don't need to memorize. Your primary, that's where you have the carbon that's attached to one other carbon. So that makes your hydrogen a primary hydrogen. It makes a primary radical because it's on the carbon that's attached to one other carbon. That's about 101. Cool. Secondary, we get 98.5. Tertiary, we get 96.5. All I'm trying to illustrate with these numbers is as we go left to right, as we increase our substitution, we are decreasing that energy of the radical. So that means that we are making a more stable radical. But what that also means is that we are starting from the weaker bond. So it is the higher energy initially goes to that more stable, lower energy intermediate. So I can look at my more stable intermediate and know that my bond must have been weaker. Because if I make the more stable intermediate, then it was easier to break that bond, so it must not have been stable to begin with. Here, we see our stronger bonds, the lower energy, so then it takes more energy to break it, and that makes the more reactive intermediate. That's what we're seeing, is this that relative stability and strength of our like initial to the intermediate. Is if you're starting with a weaker bond, higher energy, you go to a lower energy intermediate. That's the trend that we're trying to see. So we can look at the stability of the intermediate or the starting material and know what the other is going to have to be, right? Because it's going to be that opposite trend. With our carbocations, we are going to see a general trend that matches our carbon radicals. So for the most part, until the very end of the semester, we're going to ignore radicals. We're done basically talking about radicals. Now we're just going to look at carbocations. Our radicals and our carbocations follow the same trend, where we see that that primary is less stable than our secondary, which is less stable than tertiary. With that, we also see that those aliphatics, meaning that there is no resonance, are going to be less stable than our allylic, which is where you are one atom away from the double bond. You get resonance. That is less stable than our benzylic, which is where you are one atom away from your benzene. Within the allylic, you still get that primary, secondary, tertiary ranking. And then within benzylic, you also get the primary, secondary, tertiary ranking. So we're seeing this general trend of a primary allylic is going to be more stable than a tertiary aliphatic, right? So you get that primary, secondary, tertiary ranking and a general overarching of aliphatic is less stable than allylic, which is less stable than benzylic. Our carbanions, carbon with a negative charge, are going to be the exact opposite trend. So now it's going to be the primary is now more stable than the secondary, which is more stable than the tertiary. But it has this weird caveat where it is still going to be more stable to be allylic and even more stable to be benzylic. So our allylic and benzylic are still more stable. Hopefully, in your mind, you're asking, why are we seeing this trend? Like, why is it that it's the 1, 2, 3? Why is it aliphatic, allylic, benzylic? The rationale is going to be thus. So we have 3 factors that stabilize our carbocations, and therefore kind of can also help destabilize the carbanions and also help stabilize our radicals. So the carbocations, the greatest, strongest factor that stabilizes your carbocation is resonance. Yay, our old friend resonance. That delocalization of electron density through unhybridized p orbitals. That is what is making it more stable to be allylic and benzylic. So allylic and benzylic are more stable than aliphatic because they get resonance. And then benzylic is more stable than allylic because it gets more resonance. The more resonance you have, the more stable you are. So when we look at our allylic carbocation, we see that even distribution across all 3 atoms. That allylic, again, being that 1 carbon away from the double bond. Our benzylic, we see even more resonance structures. We're just going to draw one of them. Where you can now move that positive charge all throughout that ring. So our pi bonds, these are electron donating groups via resonance, meaning that they're going to push electrons towards that positive charge. Donating, giving electrons. They're going to push electrons towards the positive charge, and that is stabilizing. Our electron withdrawing groups, conversely, are going to destabilize. So anything that is going to pull electron density away from already not having electrons is going to make it less stable, higher energy. So if we think about this electron withdrawing group, something that is pulling electron density away from a site where I already don't have electrons, that is especially destabilizing. Higher energy, less stable, less favorable. So resonance can help stabilize our carbocations. It could also help destabilize. And that's what we're seeing there. The other two factors are hyperconjugation and induction. These two factors are what are giving your primary versus secondary versus tertiary trend. So the resonance is what gave that aliphatic versus allylic, versus benzylic. Resonance is what contributed to that aspect. Hyperconjugation and induction are why we get that primary, secondary, tertiary trend. Hyperconjugation is that delocalization of electron density through space. It is going to be from a sigma bond to an empty or partially empty, unhybridized p orbital. It's where we get these parallel bonds. So actually here, we'll show it as the true sigma. So that is our sigma. That is parallel. That is going to donate electron density in towards the empty p orbital. The more parallel bonds I have, the more I am donating electron density in, the more stable I will be. So for each of those, we are seeing, actually, wait, that's, here's my sp3 plus my s. Forgot it's a CH bond, so I drew the wrong sigma orbitals, I'm sorry. They essentially look like just massive hybridized orbitals. There we go. Because it's the S plus the sp3, that's my sigma. Anyway, it's just the point that it's parallel. The more of them you have, the more it's donating in, the more stable your carbocation becomes. So that's why tertiary is more stable than secondary, which is more stable than primary, because the more substituents you have, the more you're donating a little bit of electron density in through space, from this parallel orbital to that empty p orbital, through space. The donation through your sigma bonds, that is induction. So induction and hybridization kind of go hand in hand because you're going to have both simultaneously. It's just hyperconjugation specifically is through space. Induction is specifically through that sigma bond. We can have electron donating groups via induction. They are going to push electrons towards the positive charge through that sigma bond. So it's just through the bond itself. So again, the more sigma bonds you have, the more carbons attached, the more stable you become. Because the more you have, donating a little bit of that electron density to help stabilize the positive charge. Electron withdrawing groups are going to destabilize our positive charges because they're going to pull electron density away. So this induction via electron withdrawing groups, that's the induction that we talked about when we were looking at our acid and base reactivity, because we only really looked at it from the standpoint of an electronegative atom. So that was where if I get this positive charge, and I get, say, like a CF3, now I'm pulling this away. I'm pulling electron density away. That's trying to make this positive charge, this already vacant site, even more positive. That is extremely destabilizing. However, if you have a negative charge there, then that was what we saw with our conjugate bases, then that was favorable, right? So it all just depends on what charge you have there and looking at this push and pull aspect, right? The more you can spread out electron density, the more stable you are. But if you lack that electron density, you don't want to try to pull away from an already empty site. That's not going to get you anywhere. But if you have that empty site and you push in, that is going to stabilize you. So your R groups, your alkyl groups are going to donate via induction, which is why tertiary is more stable than secondary, which is more stable than primary. Cool? We all right with this concept? All right. Our reaction coordinate diagrams are where we're seeing this general reaction happen, where we are looking at energy on the y-axis, reaction progress on the x. So that means that we start over here, these are our starting materials, and we're going to see the reaction occur ending up with our product. There is one transition state for every step. So every time you get to your intermediates, you had to have a transition state. Going from your intermediate to your product, you get another transition state. Your transition states are drawn where you get the partial bond making, partial bond breaking. So you get the dotted lines showing that bond breaking, bond making. You also must have that double dagger to illustrate that it is that transition state. So if I'm looking here, and this is my first transition state, how do I know if that is representing a bond being made or broken? Yeah, look at what you have before. Yeah, use that context clues. If you're starting with having the iodine attached and you end with iodine not attached, then you must be breaking that bond. Your transition state is not isolable. You can't put it into a bottle. You can't isolate it. It is just this high energy intermediate that you have to go through in order to get to the thing you can isolate. Your intermediate. So then when we look at our transition state 2, we're going from our intermediate to our final product. So now this dotted line is representing the bond that's being formed, because I start with no bond to chlorine and I end with a bond to chlorine. We're going to need to put partial charges on our transition state because we get charged structures. Well, potentially we'll need charges. Our Hammond postulate is what is going to tell us what charges we need, if we need charges at all. So the Hammond postulate tells us that the structure of the transition state resembles the species, starting material or product, that is closer in energy to. So when we look at these two, if I look at transition state 1, is it closer in energy to the starting material or to the product of that step? The product, right? This is shorter than that path. So it's closer in energy to the product. So Hammond postulate says it needs to look more like the intermediates than it does the starting materials. So since I see charges in my intermediates, I need to see partial charges in my transition state. So that means that I need to get this partial positive on that carbon and a partial negative on the iodine, because I see formal charges in the thing that is closer in energy to. For transition state 2, am I closer in energy to the starting material or the product? The starting material. So I also need to look more like the thing that is charged, because I need to look more like whatever I'm closer in energy to. Where I see a formal charge in my closer in energy structures, I need to have a partial charge in my transition state. So transition state 2 also needs partial charges, right? That's all the Hammond postulate is telling us. You need to know what your starting material and your products look like in order to know if you have partial charges or not in your transition state. You'll see in textbooks a lot, they'll frequently just put partial negatives just like willy-nilly, and they'll just be like, this is going to be partial negative, and that'll be partial positive, regardless of whether or not this is actually endothermic or exothermic. Usually, that is done if you don't know if it's exothermic or endothermic. If you know that you are exothermic or endothermic, then you can apply the charges because you know what you are closer in energy to, right? So if you don't know your energy diagram, then there's no way really to assign those charges. You don't know. You don't know what it's supposed to look most like. So a lot of textbooks will kind of take a little caveat and just apply partial charges wherever, because they're just saying, I don't know if it's exothermic or endothermic, so they'll just kind of use negatives wherever they want. It'll become more obvious when we do an SN2 reaction. That's particularly where you'll see in our textbook that we're going to use charges differently than how we use it in lecture, because I'm going to always give you your energy diagram so you will know if you are endothermic or exothermic. Really quickly, step 1, is that exothermic or endothermic? Endo, because my product is higher in energy than my starting materials. Step 2, is that exothermic or endothermic? Exothermic, because now my products are lower in energy than my starting materials. Cool. So when we are exothermic, meaning that our product is lower in energy than our starting materials, that is called an early transition state, because you're going to look more like your starting materials. You look more like the things at the beginning, in the early stages of your reaction. So that is our early transition state. So here, my transition state for this reaction is going to be where I see I need to break the carbon-iodine bond, and I need to make the carbon-chlorine bond, and that has to happen in the same step. So what I'm going to see is I'm getting this partial bond being made and partial bond being broken, again, simultaneously, because that is what I'm seeing is the difference in between those steps. I'm gaining a carbon-chlorine bond. I am losing a carbon-iodine bond. So that's what I'm seeing here, those partial bonds. So I need to look most like the stuff at the beginning. The stuff at the beginning has a neutral carbon and iodine, but I have a charged chlorine. So that means that only the chlorine gets a partial negative. So this is specifically what we're going to call an SN2 reaction. So in a lot of books, they'll show both the iodine and the chlorine as a partial negative. because the iodine eventually becomes negative, that's their way of saying, I don't know if I'm exo or endothermic. Because they're saying, I don't actually know what I look more like. Yeah, what's up? Yeah, so chlorine is partial negative because I'm in early transition state. I look more like my starting materials. My starting material has chlorine with a full formal negative charge. So that means that in my transition state, I need to see the partial negative charge because I see a full negative charge in my starting materials. So where you see a full charge in your starting, or in whatever you're closer in energy to, in this case, your starting material, that's where you see a partial charge in the transition state. Since your carbon and your iodine are neutral, you do not see a charge on those here. The other thing that the Hammond postulate lets us predict is the relative length of our bonds. So we predicted our charges based on what we look most like. We're also going to predict the length of our bonds based on what we look most like. The bonds that exist are going to be short. The bonds that don't exist are going to be long. So when I look at my initial starting materials, I see that the carbon-iodine bond exists. So it will be short because it exists in that initial starting material. It exists where I'm closer in energy. My carbon-chlorine bond doesn't exist yet. So that means that it's going to be long. You can think about it as essentially this chlorine is approaching, and my transition state is that snapshot of like, all right, when am I about to make this new bond? And it's as chlorine is getting closer. It's not actually there yet. So this is going to be really long because it's coming in towards it. But the iodine was already there. So that bond is short because the iodine already was there and ready to make that bond, or it already started with that bond. So because I see the bond in the starting material, that is short. If I don't see the bond, then it is long in the transition state. All right, so now we're going to do our endothermic. Endothermic is that late transition state because your transition state looks more like the stuff at the end of the reaction, towards the late stage of the reaction. I'm going to look more like my products. So what I see here is the only difference. I'm not gaining a new bond. All I'm doing is losing that carbon-iodine bond. That's the only transformation that's happening here. So I'm going to see that I'm breaking that carbon-iodine bond. So it gets a dotted line, because that's the bond that's breaking. And I need to look most like my products. So I start with the charges. In my products, that carbon has a formal positive charge. So in my transition state, it gets a partial positive charge. In my products, I see iodine has a formal negative charge. So in my transition state, that iodine has a partial negative charge. Do you think that carbon-iodine bond is long or short? Ask yourself, does it exist in the thing you need to look like? Does that carbon-iodine bond exist in the products? No. So is it going to be long or short? Long, because it doesn't exist. If the bond exists, then it is called short in the transition state. If it doesn't exist, then it is long in the transition state. So you have to know what you are closer in energy to in order to know if you're going to have long or short bonds. The Hammond postulate usually trips students up, but as long as you keep in mind just the fact that you have to look more like whatever you're closer in energy to. Like that's really all the Hammond postulate says, is you just have to look more like the thing you're close in energy to, and then that just tells you what your transition state is going to look like. Yeah, what's up? So in this case, the chlorine doesn't exist at all. So we're not drawing chlorine in our transition state because we don't have chlorine. Yeah. So we're only going to include, but okay, so in all fairness, that's a little disingenuous to say that chlorine doesn't exist because it could exist here. It's just, so the reason actually that we don't include the chlorine is because it's not involved in the bonds currently being made or broken. So in the second step, which is actually what we were seeing like up here, that now the chlorine is brought in, now we are incorporating it into this reaction. Now chlorine gets included. So we're only going to include the elements that are there in the bonds being made or broken in that particular step. Okay. Yes. It could be, yeah, so this could be the mirror image of this. Iodine could have been over here. Chlorine can be over here. It's just then you would have your partial negative with the chlorine, and your long and short labels would switch, so that then this would be long and this would be short. Yeah, it could absolutely be the other way. You can draw it in any direction. It's that relative location is what's most important. Okay. Are we cool with the Hammond postulate? All right. When we look at the stereochemistry of our reactions, we can lose stereochemistry anytime we go through a planar intermediate. Or we could say that it racemizes, it becomes racemic. So in this case, if I make a carbocation then I'm going to get to a planar sp2 hybridized intermediate, in which case my chlorine, when it attacks, can give me either attacking from the front or it could attack from the back. To give me a racemic mixture. Is each molecule, that's a weird way of saying that. I'll just tell you. Each molecule is chiral, right? I have 4 different things attached to this carbon. I have a chlorine, a hydrogen, an ethyl, and a propyl. So I have 4 different groups attached to that carbon. So it is chiral. My mixture is becoming achiral because I went through an achiral intermediate, a not chiral intermediate, because I went planar. I became sp2 hybridized. So knowing your intermediate is also going to determine your stereochemistry. So another way of looking at it is you could think about it as attacking from the top or the bottom. Both are equally as likely. So I can either get bromine on the top now, or I can get bromine on the bottom. for a quick review, is this R or S? Now my brain isn't working. It's coming out at me. That's going down. Yeah, it's R. It's 1, 2, 3, 4. This one might be easier to see. What is this one? S. It better be the opposite one, because one attacked from the one attacked from the top, the other attacked from the bottom. That's what's leading to our mixture of enantiomers, giving us the facial selectivity, the opposite attack. So when you go through a planar intermediate, you're going to lose stereochemistry at some level. You might still have a chiral product, but that doesn't mean, like, you need to lose stereochemistry somewhere, so that means you would lose it at the mixture level. All right, looking at some of our common reaction trends. In organic chemistry, everything can basically be boiled down to 3 reactions. So there is also another 2 of redox and Bronsted acid base, but those are Gen Chem topics, so I assume you already know them. So the new organic topics, the new organic reactions are substitution, elimination, and addition. And basically, that's all of organic chemistry, is one of these 3 in some order. So substitution is going to be where we go from one functional group to a different functional group. So it's like going from like a circle to a square. You are going to typically have 2 reactants that go to 2 products. You are going to lose an electronegative atom that we're going to call a leaving group. So an example of this is that reaction that we just did, where we went from having the iodine to having the chlorine attached. That is substitution. I go from one functional group to another functional group. The challenge with this is that our reagents sometimes are exactly the same as what we will see with elimination. So substitution is going to compete with elimination at times. Elimination is where you go from no pi bond to a pi bond. So substitution, one functional group to another functional group. Elimination, no pi bond to a pi bond. We're going to lose a hydrogen in a leaving group. It's going to look like the same starting materials as substitution, but you get a different product. So substitution and elimination compete with one another because they look like they have this, well, they do in this case, have exactly the same starting materials, but they lead to different products. This is why most students really dislike organic chemistry, is the unit that we're about to start, is because it's hard. Because now we're looking at, all right, is the thing going to act as a nucleophile or is it going to act as a base? Is it going to attack my carbon or is it going to attack my hydrogen? And that's going to be our job, is to know if it's going to want the carbon or the hydrogen and know which product it's going to go into. And so we're going to have different factors that are going to weigh it. And sometimes the answer is it does both. So we might get mixtures of products. That's why it gets really kind of challenging, and that's why a lot of students struggle with organic chemistry. I remember that being like the bane of my existence in Orgo 1, was trying to keep it straight. So hopefully, I'll try to make it as clear as possible for you guys, for you all. Addition is going to be the opposite of elimination. So elimination is where we went from no pi bond to pi bond. Addition is where we go from pi bond to no pi bond. So it's just the opposite, where we're starting with a pi bond and it reacts. That is addition. So we're going to lose a double or triple bond. So that would be something like this. So we start with our alkene, with our double bond, adding, in this case, hydrochloric acid, to add the hydrogen and the chlorine across the double bond. So substitution, one functional group to another functional group. Elimination, no pi bond to pi bond. Addition is pi bond to no pi bond. And pretty much all of organic chemistry can fit into one of these categories. So you want to try to see that similarities, and that'll help you know when to pick. We have a couple additional considerations, so they're called additional reactions. Cyclization can occur when you are doing either addition or substitution. And the whole point of it is just, we go from no ring to making a ring. So that's a cyclization. So you can have a cycloaddition, which is where you're doing an addition reaction, but it makes a ring, which would be something like this. So this is the Diels-Alder reaction, which we're going to talk about at the very end of the semester, right before radicals. So it's an addition reaction because we're going from all those pi bonds to no pi bonds, or fewer pi bonds. Cyclo because we're making a ring. But it's still addition, right? It's still going from pi bonds to no pi bonds. Rearrangements, we're going to see these most commonly, actually we can see these with any of ours, but we're going to see them most commonly with carbocations. So we can get this with our substitution, elimination, or addition reactions. The key part is just if you're making a carbocation. So we're going to see rearrangements where you need to go from a less stable carbocation to a more stable carbocation. We're going to see that you always must make the most stable carbocation possible. Do you have questions? Oh, okay. So we are generating isomers is all that we're doing. So here, if I see this hydrogen move over, this is going to be called a hydride shift because it's the hydrogen taking its electrons. And we're just making that structural isomer where the hydrogen was attached to the tertiary carbon, now it's attached to the secondary carbon. But that gives us a tertiary carbocation. So that's really when we're going to see rearrangements. But it'll be a part of addition, substitution, or elimination. Right? For all of our reactions all semester, you're going to be able to think through the reaction in exactly the same way. So if you approach it this way, this will get you to the answer always. It'll be slower, whereas if you can remember and memorize some of the tips and tricks that I'll give you, then it'll make it faster. But in general, if you're stuck, do this. This will get you to the product every time. This is how I passed all my cumulative exams during my PhD, was this process. Even though I had no clue what the heck was going on, I did this and I was able to get to the right product. I eventually figured out what was going on, but starting out, it was pretty rough. This is what carried me through, was I realized everything distilled down to this fundamental concept. Identify what has electrons and what doesn't, your nucleophile and your electrophile. Ask yourself, is it more likely to be acid-base, Bronsted acid-base, or Lewis acid-base, which will be nucleophile and electrophile? So when we say acid-base, we're saying Bronsted. When we say nucleophile and electrophile, we're saying Lewis acid-base. It is what has electrons, what doesn't. If you have an acidic proton, like you have a strong acid, like hydrochloric acid, then you're going to do acid-base chemistry. If you don't have an acidic proton, then you're going to do Lewis acid-base chemistry, which is where we just use nucleophile and electrophile as our labels. In general, when you're looking at your atoms, if you have a more basic atom, something that's more likely to act as a base, the atom typically is smaller, whereas if it's a larger atom, then usually it's going to be a better nucleophile. We'll look at exact trends for our bases and nucleophiles in a minute, but, well, probably next week. But yeah, that's going to be, you just need to determine, do I have an acid or a base? Cool. This will happen faster, meaning that it is kinetically favored, right? Because remember, kinetic is that what the reaction rates. If you have a lower energy of activation barrier, then you're kinetically favored. Basically, protons are really small. They fly around everywhere. So if you can do an Bronsted acid base, do it. If you have a strong acid, protonate something. That's the gist of this. All right, so you identify what has electrons and what doesn't. Step 2, make them meet. Draw a curved arrow from the thing with electrons to the thing that doesn't. So we're going to draw a curved arrow from our nucleophile to our electrophile. Or what we've been doing is from our base to our acid, right? You go from what has electrons to what doesn't. Step 3, check to look if you have violated your atom's octet or its valence shell. If yes, then we need a second arrow going away from that atom. If no, then you can just move on. So for this, remember that with our hydrogen, we said hydrogen can't make 2 bonds. So when we had our arrow go towards the hydrogen, we had to have another arrow going away from it, right? That's what we're saying, is if you are violating your atom's valence shell, then you need just another arrow going away. Don't make too many bonds to an atom. That's all we're doing. So we make them meet, we check to see if we are violating its valence shell. If yes, draw a second arrow. Don't violate its octet. Don't violate its valence shell. If no, cool, draw your products. Just draw the result of those arrows and then reassess. So then you do, cool, then we start back over and you do this process and you do it over and over and over until you get to either the product that you were given and told how to get there, or until you get to something that is neutral and stable. So you're only going to stop when you get to a neutral and stable product. Some key tips: identify the bonds that are being broken and the ones that are made. Where did my arrow start? Your arrow starts at an atom and goes to an atom that is making a bond. If your arrow starts at a bond and goes to an atom that is breaking a bond, because it all depends on the flow of electrons. Number your carbons or your atoms in general. That's going to make it a lot easier to make sure that you didn't accidentally lose a carbon. It's so easy. That sounds really silly, but it's so easy to lose carbons. It happens all the time. Number your carbons, because that's always students' greatest frustration, where they will get the question wrong because all they did was they forgot a methyl, and it like bums everybody out. It upsets us, it upsets the TAs. Like every time in the grading sessions, we're like, oh, they forgot the carbon. No, and it's wrong. Because you need to make sure you're not alchemists, we're not going to create or destroy matter. Number your carbons, we're going to consider stereochemistry, and we'll finish all this out next week. All right, have a wonderful day. Stay safe.